This video covers Trig Note 6.6. We're going to be talking about parametric equations. In the past, what we're used to doing is being given an equation that has two variables in it, so usually an x and a y. And we could graph that, and we would make a circle out of it, or a line, or a parabola, or a hyperbola. Well, in this section, what we're going to be doing is we're going to be introducing a third variable, and that third variable is called a parameter. And what we're going to be doing is then having parametric equations that have three variables, and we're going to talk about how to graph those. So we are going to be moving back and forth from parametric equations, those with three variables, and rectangular equations, those with two variables. So like I said, we're used to seeing rectangular equations which have two variables. Normally we'd see an x and a y. But in this section, we're going to have three variables. We'll see an x, a y, and a t, or sometimes we'll see an x, a y, and a theta as our third variable. So that's going to give us then, three variables to deal with. So here's an example of a equation that has a parameter in it. Notice that you have an equation here, x equals t minus 1 and y equals t over t minus 1. So we can see that our third variable is the t here. So if I'm asking you to eliminate the parameter, what we want to do is we want to make it so that we're used to graphing in terms of a rectangular equation. So a rectangular equation will have only the x and the y. So I'm going to have to eliminate the t value somehow. Here's my thought process. If I look at this equation and I know that x is equal to t minus 1, and there's a couple of t's over here in this equation, my goal here is to solve this for t and then plug t into this equation. So if I solve this for t, the way I would do that is I'd have to add 1 to both sides. So I end up getting t to be equal to x plus 1. If I plug then this x plus 1 in for this t and that t, I end up getting y equals x plus 1 in the numerator, and then x plus 1 minus 1 in the denominator. Simplifying this, what I'm seeing is going to happen is my 1's will cancel out, and I'll have y equals x plus 1 over x. I can graph this now by making a t-table and plugging in some x and y values. So let's get out our calculator and either plug this into our graphing calculator and create the t-table, or do the plug and chug method where you put it in and you come up with the number on your own. So I invite you to pause the video here, input this into your graphing calculator, or just start inputting these x values in for y, and then come back and see if you're getting the same x and y values as I do. Okay, so I took a second to plug it into the graphing calculator, and these were the values that I came up with. Notice that at 0, an x value of 0, I got an error. That should make sense to us because if I plug a 0 in here for x, I get 1 over 0, which is undefined. So your graph will have a asymptote at 0, so your graph will not exist. So you're going to get two different branches of this, and so this is going to end up being a hyperbola. So let's actually start to graph these points. Negative 4.75 would be about here. Negative 3, 2, negative 1. And at 0, there was no graph. So we're noticing that we're going to have a branch that will look like this. It will approach 0, but it will not touch. And this branch will continue to go out this way. Then the second branch would go at 1, 2, 2, 1.5, 3, 1.3, and 4, 1.2. So you can see that this branch is approaching this value of y equals 1, but won't touch it. And this side will come up and approach 0 here, but it will not touch it. So this is what our hyperbola is going to look like as a rectangular form. Okay, my next example, I have x equals 3 times the cosine of theta and y equals 4 times the sine of theta. So I know that this is a parametric equation because I have an x, a theta, and a y. So those are my three equations. And I want to change it to a rectangular equation. Now when you have a theta as your third parameter, it's going to be very helpful to remember this identity. So this is the Pythagorean identity, sine squared plus cosine squared equals 1. And what I'm going to end up doing for this problem is that I'm going to solve both of these for the sine and for the cosine, so then I can have this identity and work with it that way. So if I solve the first one for cosine of theta, and I'll solve this one for sine of theta. So if I solve this one, this is being times by 3, so I would go through and I would divide by 3. So I'd get x over 3 equals the cosine of theta. Over here, because it's being times by 4, the sine is being times by 4, I would divide by 4. So I'd get y over 4 equals the sine of theta. And since I know that there's an identity out there that says that sine squared plus cosine squared is equal to 1, let's make those substitutions. Let's plug this in for the sine squared. Let's plug this in for the cosine squared and set it equal to 1. So now substituting into this identity, we would get y over 4, that whole quantity would be squared, plus x over 3, that whole quantity would be squared, and it would equal 1. If I square both of these, the numerator and the denominator, I get y squared over 16. Here I get x squared over 9, and that's equal to 1. This is my rectangular equation, and if I want to graph this, I don't need to make a t-table like I did in the last one, because I should be able to look at this and say this, because it's got two squared values and a plus in the middle, has to be an ellipse. It's an ellipse and not a circle because these values are not the same. If these values are both 16, or if they were both 9, it would be a circle. So the rules for ellipse is that a is always the bigger of the two, so this would have to be my a squared, this would have to be my b squared. The center, the hk value, is going to be at 0, 0. If a is underneath the y value, that means it's elongated vertically. So when I put my a value, which is actually going to be 4, I want to have my 4 going up and down. My b value, which would be the square root of 9, 3, would go left and right. So from 0, 0, I'm going to go up 4. That's a vertice. And that's a vertice. And I'll go right 3. Oops, that's a covertice. And left 3. That's a covertice. And now I can go through and connect my dots to make my ellipse. So it looks something like that. So when your third parameter is theta, you're going to have to try to remember to use this identity that sine squared plus cosine squared is equal to theta, and that's how you can eliminate the cosine and the sine out of this entire equation and get it into something that you're used to being able to graph. Okay, so taking a look at this next one, it says write the rectangular equation as a parametric equation. So when I look at this, what I'm noticing in both of my equations is that they both have x's. So my thought process is that if I solve it for x and then substitute that value in, I can get the x to go away. So if they both have an x in common again, and I solve this for x, it's already done for me. So now let's substitute in for this x what it is really equal to. So t would be equal to 3 minus the quantity 3y minus 2. If I use a distributive property, I get 3 minus 3y plus 2 is equal to t. And now t is equal to 3, no, if I combine like terms, I get 5 minus 3y. Now typically what we'll do once we have this solved, in this case we've eliminated the x and we have the t and the y in there, we will write it in terms of a y, because that's used to how we're seeing equations set up and to being able to graph, even though we don't have to graph it. So if we solve this for y, we would subtract 5 and divide by -3, and end up getting y equals then -t plus 5 over 3. So when I went about to solve this one, it says write the rectangular equation as a parametric equation. In order for it to be a parametric equation, it has to have the t in it. So I don't want to eliminate the t. I had to look at this and say, because this equation has an x in it and this equation has an x in it, that's what I can make substitutions with. If they both had y's in it, then I'd solve for y and make the substitution. But for this one, because they both had x's, I solve for x and then I substitute in for x. Because my final answer has to have, if it's a parametric equation, it's got to have that third variable in it. Has to have a t, and this one does. Okay, so taking a look at our next one, it says write the rectangular equation as a parametric equation. In other words, it means I have to have a t in as my final answer. So for this problem, what I'm going to choose to do is I'm going to solve, because again they both have x's in them, I'm going to solve this side for x. And then I'll substitute it in over here. So if I solve for x, I would subtract 3 and get t minus 3 equals -x. So x would be equal to a -t plus a 3. So let's plug that in now for the x in the first equation. So if I have y equals -t plus 3 cubed, I'm going to have to make this into a problem where it's -t plus 3 times itself 3 times. So I'm going to have to FOIL this. T squared minus a 3t and minus another 3t makes -6t, and then plus 9. And then I have to multiply that by -t plus 3. So to do this, I'm going to end up making my my table over here, where I put one of the polynomials spread out horizontally, and the other one spread out vertically. And then I can go through and make my table to multiply these together. So I'm going to get -t to the third plus 6t squared minus 9t plus 3t squared minus 18t and then plus 27. So combining like terms, I would end up with, again, because this is what y is equal to, y would be equal to a -t to the third. Let's cross it off so don't try to use that again. These two would make a 9t squared. These two make a -27t, and then plus 27. So this would be my parametric equation because it has t values in it. So again, when you're trying to write it as a parametric equation, you're trying to get the third variable to come into the equation. And in this case, the way I had to do it was to eliminate the x's. And then make sure that your final answer is solved for y. So mine has y equal to something, so I know I'm good.